matter research. Some people will use the more intuitive units of bar, of course, 1 bar being atmospheric pressure and 10 kilobar then, of course, being 10,000 times the pressure. Most of the high pressure research actually happens in the context of geosciences. I've got collaborators, and I'll point that out later, who are working in Bristol in the geosciences, and they are, of course, interested in pressures that are either somewhere in the upper mantle or maybe even down to the inner core of the Earth. The Earth has the maximum pressure at the core of the Earth is about 370 gigapascals. Planetary science there it goes a bit higher. So in our solar system, the highest pressures are in the core of Saturn, I think, of the order of 500, 600 GPa. The pressure scale is, of course, a very large one. One can go from very good vacuum in the lab, best vacuum that can be achieved is of the order of 10 to the minus 18 bar. Intergalactic space is a lot better a vacuum, in fact. At sea level, we've got 1 bar. The lowest point in any of the oceans is about 1,000 bar. And it is only in the mantle and core of the Earth that we're reaching those pressures that we do, in fact, realize in our experiments. I'm going to show pressure experiments today that have been performed at 150 GPa. So that's about halfway down to the core of the Earth. And as I said, the core of Jupiter is quite a bit. Actually, I've got this wrong. It's an order of magnitude more than at the core of the Earth. I'm not sure who actually put the black hole there, but never mind. So let me first look a little bit at the methods. And there's 2 main types of pressure cells that are used for condensed matter research: piston cylinder pressure cells and diamond Anvil type pressure cells. Piston cylinder cells, as the name suggests, is essentially a cylinder, thick-walled cylinder, sometimes double-walled, but that's technical details, where the inside volume is plugged on one side, and then one has a piston from the other side that one uses to compress a sample space, and where typically we, of course, don't just have a sample, but also a pressure medium, and I'll come to that later down the line. Maximum pressure that is frequently generated for condensed matter research for quantum materials or so is of the order of 3 GPa. Beyond that, one would have to have enormously thick cylinders, and then one can't stick it into a cryostat anymore, and so on. So that's why 3 GPa is pretty much the practical limit for piston cylinder cell work. Anything beyond that is based on the Bridgman Anvil type, so taking 2 anvils where we focus some force on a small area, and we're pretty much really playing P equals F over A. If we want to have a larger pressure, we make the area on which we focus the force smaller. Between these tips of the anvils here, the flat tips of that's the culet of the anvil, we place a gasket, which then seals off a volume in which the sample lives. And again, we try to use a pressure medium that ensures as good conditions, hydrostatic conditions as possible, but I'll come to that later. The maximum pressure that is achievable with such diamond anvil type cells, or more general with anvil type pressure cells, depends both on the strength of the material as well as on the size of the culet. So strength of the material, cheaper but still strong materials like tungsten carbide give you 5 GPa. Alumina, sintered alumina cells, again 5 GPa. Sapphire, you can practically go to about 10 GPa. Moissanides, which is the gemstone name of silicon carbide, single crystalline and silicon carbide, can get you to practically up to 20 GPa. And beyond that, only diamond is left, because diamond being the hardest material and hence giving us the highest pressures. Designs have been adapted to make the diamonds reach higher pressures. One can imagine just a flat culet, like indicated here. That maximum pressure with that is about 100 gigapascals. If one wants to go beyond this, one needs a bevel. So that means the slope of the anvil is stepped down before reaching the the flat culet. For this, the maximum pressure is about 250 GPa. If one wants to go beyond this, one has to shape the anvils in a toroidal fashion, that's indicated here, because at high pressures, the diamonds themselves start to deform, and this essentially anticipates the deformation that's going to happen and counteracts that, and hence increases the strength and the strength of the diamonds at high pressures. Limit for toroidal type cells is about 450 GPa. And I'm going to say something about the sample spaces later on. Recent records have been achieved by putting double anvils. So that's using one set of diamond anvils to apply pressure, and then some nano-sized spheres of diamonds have been cut in half, and the two semispheres have been put on the opposing anvils, as it is shown in this sketch. And between the tips of those spheres, one can then achieve pressures up to 1,000 gigapascals. So that's the current limits in static pressure. I'm not going to talk about shock waves pressure. There's, of course, a lot of experiments that are done by simply compressing with explosions. But that's, I believe, not so much of interest to this community, because that excludes access to low temperatures and also pretty much all experimental probes.
What's roughly the price tag of these diamonds?
I'll tell you a bit about what the price is for our pressure cells when I come to our design.
Then are these people-made diamonds, or are they mined in Congo?
Both. So you immediately, the last word, you opening the ethical dimension of this research. Yes. Both is possible. You can buy diamonds of different shapes and of different origins. There is a good reason to actually use synthetic diamonds, because they are more reliable and lower in impurities, which is good for many experiments. I'll talk about that later. But also in terms of, I've made the case that we need to go small. One could now say, okay, let's just scale everything by a factor of 2, and including the force, and hence you would still get the same pressure. But that doesn't work, because you'd also increase the number of imperfections in the diamonds by 2 or 4, if you think about area volume. And hence you've got more likely a failure. So it doesn't work by going bigger. So impurities are an important consideration. So that's a case for artificial diamonds. Nevertheless, economically, it's for many experiments, there are variants of diamonds which are cheaper to use than natural ones. And there's, in particular, we use, wherever we can, we use what's called modified brilliant cut stones. They are mass produced. I don't know whether we buy them from a company who says that they are doing this in an ethical way, but I'm not 100% sure, to be honest, about this. But in most cases, artificial stones are still more expensive than natural ones, about a factor of 2. Right. So yeah, this curve shows a bit the recorded the record pressures that have been achieved as a function of the culet diameter. So that's this diameter of this flat bit at the front, which of course does set the sample space and hence the sample size. And you can see that with single bevel, one can, without a bevel, one can get about to 100 GPa, and beyond that one needs double bevel, and the slope goes down a bit. Okay, so let me come back first to how pressure cell experiments are set up in piston cylinder cells, because I started with that. Electrical transport measurements are one example, which I've done quite a bit. Essentially what you do is you make a feed through where you've got the wires going through the closed plug. Here the principle is that you pot the wires in with some epoxy which contains sapphire powder itself, and because it becomes narrow, you essentially, as the pressure is applied, the sapphire grid is compressed and is essentially stuck. Like you could if you think of an hourglass, if you've had some larger grains of sand, it would gridlock in there. And that's the same principle here. And then inside the pressure cell, you've got a sample space about 10 millimeters long and 2 millimeters in diameter. And nevertheless, you can put these pressure cells into highest magnetic fields and into cryostats down to lowest temperatures. And hence you can conduct many experiments. So I've got here pictures of samples that have been mounted for resistance measurements or even for Hall effect measurements where the sample is actually living on this end here. And this guarantees the orientation relative to the magnetic field. And these experiments have been very important. So for instance, all the work on the cerium palladium-2, which is the prototypical quantum critical superconductor, that has all been done in piston cylinder cells. And there's a lot of reliability and a good success rate for piston cylinder cells. It's still fiddly because we're talking about sub-millimeter samples or millimeter size samples and getting all the wires and everything arranged, but there's a good success rate with that. Diamond anvil cells, it gets a bit more tricky. So this is a design of the diamond anvil cells that we use. It is 14 millimeters in diameter and about this high, so about 3-4 millimeter high. A lot of the construction is about making sure that the diamonds are well supported without any chance for them to tilt relative to each other or shift relative to each other, because if the culettes don't meet each other, then then the diamonds will end up crushing each other. So it's surprisingly easy how you can actually chip two diamonds by having them touch each other on some edges. One has to be quite careful that one never does this also in the preparation steps.
Are the techniques to make contacts under high pressure very different?
Yes, I'm gonna that's my next step. So we want to ensure that the two diamonds are nicely opposing each other, and that's most of the construction. But then, of course, we want to do some experiments, and we want to do, for instance, electrical transport measurements. And what we've done in my group, and we're well established now, is that we deposit electrodes on the diamonds, as it is sketched here. So we have those electrodes running on the diamonds from the outside, from the girdle, all the way to the center, to the culet. Down here, this is a picture which shows a sample at pressure inside the pressure cell, which is sitting, we're looking here from this through the diamond that has got the electrodes on it. So you can see these gold electrodes coming in from 6 directions, and then silver paint or other conductive methods can be used to make contact between the electrodes on the sample at the inside of the pressure cell, and then the outer bit of the electrode is freely accessible, so you can attach a standard wire to that and hence use those electrodes to inject current and detect voltages, for instance, for magnetoresistance or resistance measurements, magnetoresistance, Hall effect measurements, any transport measurement that you could imagine, electrical transport measurement.
How do you know what the pressure is that you are?
I'll come to that. One challenge with the electrodes in the diamond is that we used gaskets. You do need a gasket indeed, both in order to confine the sample space as well as to protect the anvils. In fact, we use metal gasket. We need the malleability of metal for that and the tensile strength of metal, such that we can indent with the diamonds into the gasket without it splitting. If it was to split, the diamonds would touch each other and they would just crush each other. So we really need this strong, high tensile material, yet with some malleability to provide us as a gasket. So there's no way, pretty much no way around metal. And that, of course, causes the problem that this gasket sitting right on top of the electrodes would immediately short anything. That means we also need an insulation and a thin insulating, electrical insulating layer. I've sketched this here as sitting on the anvil, but in most experiments, we actually put the insulation on the gasket itself. We produce this from insulating materials. Depending on what pressure we want to, we have to keep in mind at what pressure some materials might become metallic. So most of the time use or nitride or aluminum oxide, which stay insulating to quite high pressures. The high pressure cells lend itself to miniature microprobes like combination with FIP. So here is a picture of a sample that has been FIP cut and contacted directly on an Anvil to electrodes that have been evaporated on there. So there's some good experiments when one can do this way. It does, of course, multiply the success rate of the success rate of FIP and high pressure. So one has to keep that a bit in mind when doing such experiments. But one can engineer some nice things here. I've already essentially said what pressures we can achieve, but here again an overview of what that dictates in terms of sample size. So if the culet is say a millimeter in diameter, that means of course the sample space can only be half of this, because the hole in the gasket roughly is half the diameter of the culet itself. So that means for 10 GPa culet of 1 millimeter, we've got a sample space that's about 500 micrometers, and that corresponds to the hole that's visible here in this picture. The transparent region is all the hole in the metal gasket. This outer bit here is the metal gasket itself. You can also see here the semi-transparent region, which is the insulation, which has been put on the gasket. And then what is transparent around the sample is indeed the pressure medium. And I'll discuss that further down the line a little bit more. But if one wants to go to pressures relevant for hydride research, we need to go to culet sizes of about 50 micrometers. And this dictates that samples cannot be more than 25 micrometers in size. Okay, so how do we make these electrodes? Mostly we do this with a masking technique. So here again, the setup of two Anvils with insulation and some metal gasket. In order to produce these electrodes, what we do is we take the Anvil and we use a shadow mask, which has been laser cut, and sometimes we make the finest features then simply with some fine wires. We evaporate through these shadow masks, and hence we end up with electrode configurations like this. So this is now an Anvil that has been prepared indeed for hydride research. So it's a 50 micron, no, this is a 100 micron culet. And this is then what you see once you look through the whole of the gasket on top of this mask. So you can just about see the tips of that sample. The thin film deposition itself requires a bit of optimization, but we've got that very well under control now. Very good adhesion of the electrodes, and barely ever problems that they short to the gasket or something like that. Pressure medium, we've had that question already. Ideally, we want hydrostatic conditions. Most often we want hydrostatic conditions. Sometimes we might be interested in some uniaxial pressure, but generally we want hydrostatic conditions. And of course, that's something which is very easy to model. So hydrostatic conditions requires a liquid pressure medium, because liquids, of course, have zero shear modulus, and hence they will always convert the unidirectional force that we exert to the back of the Anvils into a hydrostatic isotropic pressure. So we want liquids, and the best liquids we can imagine are, so here are pressure mediums listed in order of descending quality. Helium, hydrogen are best pressure media, neon, argon, nitrogen, so all noble gases and gases, then materials that are already liquid at ambient conditions, but where they have been essentially mixed in order to avoid crystallization and hence suppress solidification of these materials. But none of these, including helium, are liquid above 25 bar when it comes to low temperatures. So anything will be solid at the moment we start to do low temperature experiments, which isn't necessarily a big problem. Helium or even argon is actually quite a soft solid. So if you ever try to manipulate solid argon, it feels a bit like butter. It's quite soft. So that means shear modulus is small, and non-hydrostatic conditions are still quite small. And one can also make sure that one changes pressure only whilst the pressure medium is liquid, such that it such that one avoids squeezing on the sample whilst the pressure medium is solid. Nevertheless, sometimes signatures are visible in samples that are due to the pressure medium. This is data that I've actually shown yesterday. Yesterday, I've drawn your attention. This is titanium diselenide. I've drawn your attention to the charge density wave transition, but I've not been talking about this shoulder here, which is also visible in the derivative. And that's exactly the freezing temperature of the pressure medium. So if we trace that through the phase diagram, it's a straight line with the zero pressure intercept being the freezing temperature of glycerol, the pressure medium used, and this intercept here at 5 GPa and 300 Kelvin being the solidification pressure exactly known for glycerol. So sometimes one can see this, and some materials are more sensitive to this than others. You can probably easily imagine that a transition metal dichalcogenide is van der Waals compound is quite sensitive to any non-hydrostatic conditions in the C direction.
Question, please. Isn't it when glycerol solidifies, it becomes glassy? So is that a worry that it's glassy?
Never, actually, glassy sounds good because it gives you it keeps the shear modulus low, but nevertheless it has a shear modulus even when it's glassy. So it in the sense of a pressure medium, it is not really bad, but it already disqualifies itself as a liquid. It's not a liquid anymore. Even glasses have a shear modulus.
So glassy, but glassy is better than not.
Crystalline is certainly worse because then you've got a tensor, and you can have quite some more pronounced effects. Yes. Okay, measuring the pressure. Actually, I don't have a slide to this, but I want to answer Jörg's question. So there's different ways to do this. One way is actually indicated on here. So here I've got a strip of lead inside a piston cylinder cell, contacted up for resistance measurement, and one can simply trace the superconducting transition of the lead, which is known how it responds to pressure. In fact, that relates via thermodynamics to the volume change at the transition temperature. So that's quite well known and hence understood, and one can use this as a pressure gauge. Then other pressure gauges, fundamentally there are primary pressure gauges, like calculating the lattice constants of sodium chloride from first principles as a function of pressure. You could use that by doing X-ray diffraction, measuring those lattice constants. You can figure out the pressures in a pressure cell with essentially a primary gauge. Many secondary gauges, pressure gauges are available at highest pressures. In diamond Anvil cells, we often place a tiny bit of ruby. So there's a chip of ruby here right underneath this cursor, which you can shine a green laser or some high energy laser on to excite the fluorescence, record the fluorescence, and it's in red, of course, because ruby is red. And that shifts as a function of pressure that has been calibrated before. So we can this way figure out the pressure. It becomes too low in intensity and too broad above 50 GPa. From 50 GPa onwards, what we use is the diamond itself. The diamond has a vibron, which is visible in Raman. And actually, I've got some data later where I'll point this out, which is visible in Raman and which does shift as a function of pressure. As the pressure is increased, this diamond lattice becomes more stiff, the vibron goes to higher energies. And by detecting the Raman signal of this, focusing on the diamond very close to the sample, so essentially to the culet, we can detect the pressure at the sample. Right, so then let me maybe just as a brief background, just illustrate what we can hope to achieve with pressures. And what I'd like to highlight is that the energy density that we can get with high pressures is quite high. What I've got plotted here is the compressibilities of a few materials, just some elements. Diamond, no surprise, is here least compressible. Helium is the most compressible, but in between quite a few elements that are not completely vegetables, some of them having interesting things like bismuth. The area under these curves is the energy density that we work onto the material. And integrating up this curve gives you that 10 GPa is about equivalent to 1 electron volt per atom. So that's quite a bit of energy that can shift around electronic states. Of course, we can't control to shift specific orbits in a specific direction. The material will rather optimize itself to that, but the high energy densities that we have available give hope that that's a lot of things can happen, and it's in particular about 1,000 times larger than what you can achieve in lab magnetic fields. And we do create new phases, and I'll show the example of the hydrogen sulfur later on. We can try to understand ground states, how they interact with each other, and I'll show some results on elemental sulfur. Or we can tune some energy scales like in MOT insulators, and I'll see if I've got time to just flash through what we've done on nickel disulfide. One other important property of high pressures is that if we do indeed manage to have hydrostatic conditions, it's isotropic, and hence it's reasonably easy to model this in theoretical or ab initio work, namely by simply changing the lattice constant. And I'll show that. I've shown yesterday already some DFT results that we've obtained on titanium selenide, but a lot of the community uses this to find new structures, to predict new structures and evaluate which ones could be interesting, for instance, for high temperature superconductivity. A key piece in this is the equation of state. If you simply, I've made the case that the volume versus pressure is the energy density that we've got in the material. And hence, it's very interesting to look at the volume to get a starting point how to understand materials. So here, for instance, is lattice volume versus pressure for cadmium, which you can infer, for instance, from X-ray diffraction. And fitting this gives you compressibilities as well as the first derivative of the compressibilities. And you can do this both with experimental data as well as with DFT data, where you think about where you invert this essentially to be an equation of energy versus volume, and then pressure being the coefficients that dictate this fit. So that's how one can make a very close link between ab initio models and experimental results in high pressure cells. So I'll show some examples of what we've done, and I'll actually start with some work on elemental sulfur that we've done as a side product of our work on hydrogen sulfur. So these were Raman measurements. Raman measurements are, of course, relatively straightforward because they are contactless. They actually do not require the electrodes. You can just shine in a laser and record the light that's re-emitted from the sample. It requires some optics, and of course that one can make it high resolution and low energy cutting, which makes it challenging in itself, but often enough one can get some good results quite straightforward and probe some of the excitations of the material. In particular, we've been able to probe the amplitude mode of the charge density wave in elemental sulfur. So sulfur, you've got it in mind that at ambient pressures, of course, as a yellow insulating material, but at high pressures at about 100 GPa, it turns into metal, nice shiny metal. And it in fact hosts a incommensurate charge density wave between about 90 and 150 GPa. This has been previously already observed in X-ray diffraction. It's incommensurate with close to with a Q vector close to 3/4, and at the same time, this phase is the underlying structure. This is also a monoclinic structure, which is a distortion of the high pressure rhombohedral structure of sulfur. And what we could show with our Raman measurements together with ab initio calculations is it's no coincidence that it is both a charge density wave and a monoclinic distortion, but they actually stabilize each other. But let me first show you the results. So these are Raman measurements. here from in the energy window or in the wave number window from 100 to 700 wave numbers, you can see several peaks, which most of them are phonons. Down here are the peak positions. You can see that many of them stiffen as a function of pressure, which is exactly what you expect. The lattice becoming more stiff. This is also true in this sulfur 4 phase, which hosts the charge density wave, except for this lowest lying mode, which is softening as the pressures increase. And this is exactly what you might expect for the charge density wave, because the charge density wave, it has been figured out earlier by X-rays that the atomic displacement reduces as you get to higher and higher pressures. So essentially this traces the strength of the charge density wave ordering parameter, and hence the curvature of the potential, and hence the Higgs mode or the amplitude mode of the charge density wave. But what's most noticeable is that it doesn't go to zero, rather it abruptly disappears at the critical pressure. And we can understand this by looking at the energetics of the two things that happen. Namely, if we start with the rhombohedral structure that's present in the sulfur 5 phase, so outside the charge density wave, you can do two things to it. You can either introduce the charge density wave 3/4, we approximate it with a 3/4 modulation, or you can introduce the monoclinic distortion, but each of them individually gives you a state that's higher in energy. So none of them individually is actually favorable. Only when you combine the two, when you combine the monoclinic distortion and the 3/4 modulation, you get something which is lower in energy. So that tells us that they mutually stabilize each other. And it is exactly this coupling which gives you this abrupt disappearance, because once they become too weak, essentially the coupling gives you a weak first order transition from the charge density wave and monoclinically distorted phase back into the rhombohedral phase at higher pressures. Down up here is the energy landscapes that illustrate this. So the x-axis is the displacement of the atoms due to the charge density wave, so the amplitude of the charge density wave, and the y-axis is the monoclinic distortion. And you can see the minimum here is at a finite displacement due to the charge density wave, and also a finite monoclinic distortion. This remains the case to some intermediate pressure, where they become where you've got then two minima separated by a very small, very shallow barrier in between, and hence you can imagine that you can have a first order transition from this minimum to that minimum, this barrier being smaller than the thermal energies, doing experiments at any sensible temperatures, so room temperature or down to 50 Kelvin even. You can imagine that the sample is just fluctuating between those two, so hence it becomes a weak first order. But then you can see it later on for higher pressure still, the energy minimum is for the no charge density wave and also no monoclinic distortion. So they are really coupled to each other. Okay.
The fact that there are no data points above, I don't know, 150 something.
No, there are no Raman active modes in the rhombohedral structure, so that's expected.
Okay. It's sad, but expected. Okay.
Yes. By sad, you mean?
It could be that you just aren't there.
No, we went into that phase. In fact, I can point out this curve down here, the lowest one, is indeed beyond that phase boundary, and there's nothing left there. So the charge density wave mode is this one. You can see it's disappeared. These phonons are this mode, nothing there, and this mode, and yeah, maybe a tiny bit there, but there's also some, I'm sorry, is that actually, no, actually it's these two guys, which are both disappearing. This is a mode which originates from the pressure medium. Okay, so with that, I'll move to the Hydride Superconductors. So we've done some work on hydrogen sulfide. And this includes both the synthesis as well as studying the superconductivity with electrical transport measurements, including in high magnetic fields. So the way we did this is by loading sulfur on a diamond anvil cell. You can see here at ambient pressure the nice yellow piece of sulfur sitting on top of the electrodes. We then prepare gasket and anvils and everything, and we load the gasket space with a hydrogen donor material. We've not used elemental hydrogen because that's quite tricky to deal with. You would, in order to get a sensible density of hydrogen in a diamond anvil cell, you need to put the whole pressure cell into a hydrogen loading system where you pre-compress to 2000 bar. That gives you a similar density as if you were to cryogenically load, but both cryogenically loading and high pressure loading have quite some serious safety implications, because having a cylinder which takes the whole cell, meaning that there's a volume inside of about a liter, but having a liter with 2000 bar of hydrogen is quite a safety concern. So not so easy to establish this. I believe there are only 2 places in the UK that do this, in Edinburgh and at Diamond Light Source. What we rather use is a hydrogen donor material, ammonia borane. This is the chemical equation, H3NBH3. You can see it contains a lot of hydrogen. In fact, the hydrogen density of this is comparable, or is actually equal to pre-compressed hydrogen or to liquid hydrogen at cryogenic temperatures. So we've got no disadvantage in terms of the hydrogen that's available there.
Does it lead to contamination with nitrogen?
It does. I'll point that out. The ammonia borane is actually a well-studied hydrogen donor material in the context of hydrogen-powered vehicles, fuel cells, all of this. Because once you warm this up to about 70 Celsius, it starts releasing hydrogen, and it does so in several stages. First, it releases one hydrogen molecule and forms some polymer, and then it releases another hydrogen and forms double-bounded polymers, and only eventually it releases all of its hydrogen and forms what's left over then is boron nitride. Boron nitride being nice and inert, so we're not too much worried about this. And in fact, we use boron nitride for our gasket installations anyway, so that is already present. So the idea being that once we heat this at high pressures, and then we can release hydrogen and make it react with our sulfur to form hydrogen sulfide. The heating is done with a laser. So we focus a laser of about 20-30 watts onto our sample. We usually heat only for less than a second because we don't want to heat up the whole pressure cell. Heating up the whole pressure cell makes the material softer, and the diamonds start then to indent into the cell body, and they then start to tilt, and we've had several diamonds explode because of the heating. So one has to be careful with that. We want to reach temperatures that are both sufficient to dissociate the ammonia borane, as well as to provide the energy to induce the chemical reaction to form H3S. Now, it's not, you might ask what temperatures are required. That's purely empirical. There's no entropy, including ab initio calculations that tell you what barriers are there between different phases. So it's purely empirical, and we usually heat samples to about 1500 to 1800 Celsius for half a second, and maybe repeat that a couple of times to induce the reaction. But it is, we can confirm for ourselves that we have got that we do have this reaction taking place by looking at the X-ray diffraction. So up here is a X-ray diffraction pattern taken on a piece of sample which has not reacted, and what we get is a pattern that's very consistent with elemental sulfur. And here we've got a X-ray pattern collected on a piece of sample that has been reacted, and I'll point out where this is on the sample in a second. And we do get an X-ray pattern which is nice and consistent with the cubic structure of H3S. this is the sample for this particular X-ray measurement. So what we've got here is in fact 6 electrodes. So it's not exactly same sample like this one. We've got 6 electrodes for redundancy, but also it allows us, as I'll show in a minute, to probe the sample in a bit more detail. We've done laser heating in one area only, which has now turned black here, whereas the rest of the sample is still in this photograph of gold metallic appearance, but actually I wouldn't say that it is necessarily goldly colored, the sulfur. That might be that the lighting here was also a bit not white light. But sorry.
Pressure, sulfur becomes metallic and superconducting itself, right?
Yes.
Do you see this too?
Yes, I'll show it. The black area is where we've done the laser heating, and the black area is exactly where we observe the X-ray pattern from the H3S. So we can, for instance, take this peak intensity and look at this in a spatial map, and we see this area here in red, which has got this H3S phase, whereas everything else has got, say, take this peak intensity, has got the elemental sulfur phase. So we quite clearly see that H3S is formed here. The black stuff on top is most likely exactly either boron nitride or one of those polymers. This one peak there, the largest peak that is not fitted by our X-ray diffractions, is in fact consistent with boron nitride. So it suggests that we indeed have boron nitride present on top of the sample. The hydrogen probably then having diffused into the sample and reacted with the material. Okay, so we've got not a uniform sample that's superconducting throughout, or not H3S throughout, but we can nevertheless start looking at transport properties, and we've been careful not to laser heat more than necessary, because every additional laser heating bears the risk of exploding the cell. That's why we've rather looked at the transport properties of this cell in more detail before we do this, and the cell still exists and data are nice and reproducible, and someday we might carry on laser heating more. But what we can observe already on this cell right now is, first of all, before laser heating, that's the blue curve here, metallic behavior with a superconducting transition at 70 Kelvin. That's exactly the elemental sulfur that you were asking about. After laser heating, that's this red curve, a large jump at about 200 Kelvin with some residual resistance present below, and again the transition to full zero resistance at 17 Kelvin. So that tells us that this residual resistance is some of the sulfur that's in the current path, and that makes sense because we've been probing with these 2 electrodes as current and these 2 as voltage, so probably this voltage lead here is sensing some of the sulfur, elemental sulfur. But we can understand the behavior of the sulfur quite well. So the dashed line here on the elemental sulfur is a Bloch-Grüneisen fit, which gives a sensible Debye temperature and a exponent of 3, where you would expect 5 for intraband scattering. You would expect 5 for interband. You'd expect 3. So we see that it's in fact intraband scattering that dominates elemental sulfur here. If we fix those coefficients that we obtain from the elemental sulfur and attempt the fit to this residual resistance, we see that that this is indeed consistent with elemental sulfur and a increased purity of the sample, and then we can subtract this. So this way we get this curve. So that's now essentially taking the red curve and subtracting this dashed line down here. Then we get the resistance contribution from this H3S bit of the sample. This assumes that we've got indeed a serial resistor network from the sample stretching on. Now we can again look at the normal state behavior of this, and again fit this with Bloch-Grüneisen. Here we find the standard exponent of 5 and a Debye temperature of the order of 1300 Kelvin, which is in surprisingly good agreement with the characteristic phonon frequencies calculated from the Eliashberg function. Now you'd say that it's probably acoustic phonons that dominate the electrical resistance, and optical phonons, which will have a large role in the superconductivity. But nevertheless, this fit is suggesting that the Debye frequency is quite high. most importantly, we can take these resistance measurements and convert them into resistivity using the approximate sample dimensions that we can observe. So about 15 micron laterally and say 2 micrometer thick. The resistivity then in the limit in the extrapolation to zero temperatures of the order of 7 micron centimeters, so goodish metal. And we can convert this using the existing Hall effect measurements into a mean free path, which comes out at about 8 nanometers. Some of the other groups have, of course, also looked at the magnetic measurements. So Michael Aramit's group, most notably, of course, they have done, they've put the whole pressure cell with a sample. Actually, they've designed a specific pressure cell for magnetic measurements and then synthesized H3S in this and mounted in a squid magnetometer, which does still require subtraction of the background from the cell, but they've done this and they see that there's a diamagnetic signal emerging at the superconducting transition. Now, let me carry on with our transport measurements. We've conducted these in finite magnetic fields, and a big question which has been raised, and particularly around by Joche Hirsch, about some of the superconducting materials that they appear to have no rounding in finite magnetic fields, but we do quite clearly see this. Let me first walk you through all of this. So we do see the transition shifting in magnetic field as you expect for a superconductor. This shift of the critical field versus temperature is in agreement with work from the Aramit's group. One should note that these are samples synthesized in different ways, namely our sample from this ammonia borane, whereas Aramit's samples were synthesized from sulfur and molecular hydrogen. As a consequence, the resistance ratio of our sample and Aramit's sample is a little bit different, factor of 2. But nevertheless, we see pretty much the same HC2 curves. That suggests us that we are independent of the purity of the sample, meaning we are in the clean limit. And indeed, if we take the slope and just use the simplest single band BCS superconductivity, we can extract the Fermi velocity of the order of 3.5 times 10 to the 5 meter per second, coherence length of about 2 nanometers, which indeed is smaller than the mean free path that I've extracted on the previous slide. So that's confirming that we've got clean limit superconductivity in these samples. At the same time, if we compare this Fermi velocity with DFT calculations, we can see that it is smaller. And indeed, it's close to what you expect due to the renormalization from the electron-phonon coupling. So you get a factor of roughly 1 plus lambda difference here. You can already see a bit of the rounding of the superconducting transition. We can have a closer look at this. So if we plot the transition versus reduced temperature, then you can see here that the rounding becomes quite clearly visible as we increase the magnetic field. The width could be characterized, for instance, as a temperature difference between 50% and the onset. It increases linearly in field with a finite intercept, and yeah, we've got a significant increase. Now, it is expected that the transition width is a function of the magnetic field. Specifically, it is actually expected that it should be a function of temperature over field, temperature to the power of 3.5 over field, but actually we do see it linear. Indeed, if we attempt to scale the resistance, so this is the resistance of all these curves plotted versus reduced temperature divided by reduced field plus a constant, where this constant essentially reflects the finite width in zero field, or this intercept down here. You can see that the data collapse over a large range, namely down to half the transition. If we were to try the same with temperature to the 3.5, there's certainly much worse a collapse. There's no collapse of the data. So it suggests that we do have some universal behavior, some temperature over field scaling here in the in the around close to the transition. Usually this is associated with flux movement, vortex movement. But as I said, traditionally it has been derived from, in theory, that it should do T to the 3½ divided by field. We don't observe this, so that is an open question what that might mean for the superconductivity here.
What's the numerical value for alpha? It's dimensional,
Point-
so it should be a number, right?
Yeah, 0.019.
Ah, okay.
So it's small compared to H. And you can see this because the intercept here is small compared to the dynamic range of the broadening. All right, so that's what I've got to what I'd like to say about the hydrides today. Do we have time? Should I show a little bit about our MOT insulator work under high pressures?
Maybe a good point to stop the questions from.
Yeah.
So one question is, so these are multiple domains or single crystal? Can you say that? And the same question actually, is there a notion of which direction does the field point?
It is, it's a polycrystalline, and this X-rated pattern in particular is fit with a Rietveld refinement, which assumes a powder sample with zero texture in there, and it's quite a good fit. So you can see that the intensities, so the significance is here the intensity of the peaks. The expected pattern versus the observed pattern is very close in intensities, and that tells us that it's quite a good polycrystalline sample, meaning that the domain sizes are smallish, not too small, but we've got definitely a good a large ensemble of different crystallites in that polycrystalline sample. We have not looked at the second question was about the orientation dependence of the magnetic field. We're limited to one orientation because our pressure cells are long cylinders, as I've shown here, specifically made such that they fit into the magnetic field with the field along the axis of the cylinder. We could, in smaller fields, we could potentially rotate a little bit, but not by more than 10, 15 degrees. But we've not yet done this. And whilst the sample is certainly not a sphere, it's about 50. The H3S phase is about 15 micrometer laterally and about 2 micrometers thick. But this is not an enormous anisotropy, and it's not an enormous demagnetization factor. So I don't expect much dependence on the orientation of the field here.
You want to remind us briefly what the objections from Hirsch were?
So for several of the materials, Hirsch has disputed whether there is a rounding in finite field, as you would observe for superconducting transition. I mean, fundamentally, this slide relates to the two probes that are typically done for superconductors, namely looking for zero resistance and a perfect diamagnetism. Now, both of them have got resolution limited. In an experiment, we're always limited somewhat to resolution. So in the resistance measurement, we have subtracted, I should be honest about this, we have subtracted a residual contribution from the sulfur. So we've not got the claim for zero resistance of the H3S phase in this particular sample. Aramets has got this claim. So he has produced samples which showed in his experimental resolution zero resistance. You could then look at the noise of these experiments and hence extract what's essentially an upper limit for the potential residual resistance that's still in there. And that's of the order of nano centimeters in his samples. Hirsch has criticized the work of Ranja Diaz on the carbon sulfur hydrogen, which was published in Nature 2019. He's criticized that much more. And there is some reason to that, because if you look at the resolution of what they call zero resistance state, it's more of the order of a microohm centimeter. So their measurements would be consistent with something coming from a bad metal to a good metal. Whereas Aramet's work and other work on the hydrides indicates that it would have to be an extraordinarily good metal that we go to. Diamagnetic measurements are extremely hard to get absolute values. First of all, the background subtraction is tricky with the pressure cells. The next challenge is if you were to convert that into a magnetization rather than just a magnetic moment, you need good understanding of the demagnetization behavior of the sample. And that's very tricky to get, because for that you would need to know the geometry quite accurately. And hence, this is not an absolute measurement. It's a drop in the magnetic response, but not an absolute measurement which shows you a susceptibility of -1. In the work of Ranja Diaz on the carbon sulfur hydrogen, they have shown a drop in AC susceptibility. This has been criticized by Hirsch for the fact that the curve had a drop at the roughly expected temperature, but it had other larger features at different temperatures. And there has been further criticism that some of the data looked suspiciously similar to an earlier measurement of the co-author who had done the magnetic measurements. Yeah, so there's criticism on essentially about how confident are we that these probes are accurately probing superconductivity. Unfortunately, then it's not so easy to come up with other probes. At ambient pressure, you would do specific heat, but that's virtually impossible. I don't see a way to do that in a diamond anvil cell on a 15 micrometer sized sample.
Maybe this is how incredibly important it is to reproduce this. So
Yes.
maybe.
Yes. Okay.
Can I ask a question?
Of course.
Do you have estimates of, you've got the electron phonon coupling because you fitted the resistivity, right? And when you play with some of the standard formulae for TC, do you get an estimate of what U star should be in the system?
Evgeny Talentsev has done this quite in some detail. Essentially, he's cooked up a global fit function which includes the step at TC and hence extracts TC and takes the electron phonon coupling, and he comes up with a variation of Coulomb parameters, but typically of the order of 0.15, 0.13. So it is similar. It's smallish, yes. Small. But yeah, I mean, there is reasonable uncertainty because in order to extract the electron phonon coupling, we need to take into account the geometry of the sample. And of course, there's always a reasonable uncertainty in the thickness of the sample because we can't really measure this. We can only guess this based on what we think is happening under pressure. And hence, there's easily a factor of 2 uncertainty on the electron phonon coupling if we were to extract it just from the resistance.
And what are the difficulties, the sense of the difficulties of going the next stage to the yttrium hydrides? Is it just a great, or the difficulties of pushing this up to room temperature?
So the lanthanum hydride, LaH10, is what was the record before the carbon sulfur hydrogen work, and yttrium H10 is very similar transition temperature, both around 260 Kelvin. They have the difficulty that you can get multiple phases. So maybe I should let me swap to another. Let me get out some other slides about this. Is this coming through? Yes. So for lanthanum H10, these are data reported by Aramet's group with a resistive transition at about 250 Kelvin and a diamagnetic signal at a similar, in this case, a bit lower temperature. The challenge with these materials is that you can form multiple phases. And what typically is looked at from an ab initio point is the convex hull, which calculates the enthalpy of different stoichiometries and anything that's on a convex hull formed between the end members, which could be lanthanum and hydrogen, or here they've chosen LaH2 as the lowest binary. anything that's on this convex hull is stable as a ground state. It's still a question whether or not you form this, but you can see that there are many. So you could imagine that if you just start to react lanthanum with hydrogen, you could form LaH2, 3, 4, 5, 8, 10. And then there's also some which are not so far off. So for instance, here LaH6 and LaH12 are only slight energy above the convex hull. So laser heating to 1,500 or 2,000 Kelvin, you could imagine that even those might be done, you might be trapped in there metastably with these phases. And indeed, that's what's observed. Both in resistance, you get not just the transition that I've had on the previous slide at 200 Kelvin, but 250 Kelvin, but you also get transitions in some samples at 100 Kelvin or 60 Kelvin or even 20 Kelvin only. And the resources have not been invested to try and really disentangle this. We've worked a little bit on this ourselves. We see that we can also form what you might call lower hydrides because it's not the full highest TC. So for instance, if we react lanthanum with the ammonium borane, we get some curves that have a resistive transition at about 70 Kelvin in some of our samples. We've then looked at it with X-rays and it becomes messy. We can see X-ray patterns that are consistent with lanthanum H4 in some parts of the sample, and then some X-ray patterns which are consistent with some cubic structure in other parts of the sample. And then the question arises, which one of these is what you're measuring in resistance measurements? Because you could imagine that X-ray diffraction has got a detection limit, and you could still have some filaments running through the various phases, and it becomes tricky to disentangle. And also here, what you've asked earlier about contamination, having this ammonia borane around gives you in fact a plausible route to yet another phase. Namely, you've got some boron available, which could form lanthanum boron H8, which is indeed predicted to be stable and predicted to be a cubic phase and predicted to have lattice constants, which are very close to this cubic X-ray pattern that we observe. So it's plausible that this one is present. And in fact, it is predicted to have a TC that is of the order of 100 Kelvin. We observe 70, 80 Kelvin. So it could be that one, or it could be the lanthanum H4, which is consistent with the X-ray pattern in some other parts of our samples that we see here. So it becomes, H3S has the beauty that it looks like there's only one phase that is stable, and lanthanum and yttrium are a bit more messy in that sense.
Can I ask another question?
Sure.
Oh, sorry, go ahead.
You say in H3S the transition broadens as you increase the magnetic field.
Yes.
You say how you understood that?
Fundamentally, broadening of the superconducting transition is associated with vortex flow. That's one model that has been built to understand the broadening of the resistive transition, and then there it's an energy scaling argument that if you've got vortices and you want to start them flowing, the further you go away from the transition temperature, the more it costs to make them flow, and that's why it's predicted to scale as T⁵ divided by magnetic field. There are, of course, other mechanisms that could give you a broadened transition, but many of them actually would also give you already a broadening in zero field, or it is about filamentary superconductivity, but that would actually give you a narrowing transition if you think about, or either completely suppresses your transition temperature very quickly if you've got a filament, or it gives you something which actually sharpens up as a function of field.
Vortex, and then you see depending as a function of current.
We have looked at current dependencies, but we are careful not to overdo the current densities for these electrodes. We have also already fried some contacts in some samples, so we're limited to small-ish current densities, hence we can't really easily look at deepening effects there.
My question was connected to the distant past. I've heard that at various points in the past, many famous theorists have speculated the possibility that if you made such a room temperature or high temperature superconductor, it would remain metastable when you remove pressure. Have you thought about this, and is there any possibility in the world that any of this could be possible? But if you had an ideal crystal, what would happen to one of these crystals if the pressure were removed? Would it sublimate immediately, or what would happen? Do you have any idea?
I could easily imagine that it sublimates or dissociates into hydrogen and sulfur, for instance,
Yeah.
and I don't see what would hold it from doing that. I mean, of course, we are using diamonds in these cells, which itself is a metastable state, which is stable at ambient pressure, at ambient conditions. But there's a big difference in that the bonds of diamond are very strong, and yeah, it's an insulator. It's well away from the chemical potential. Whereas in hydrogen sulfide, we have a metal, and hence we've got some bonds. In fact, important bonds for the superconductivity, antibonding states of the hydrogen sulfur bonds. We've got them right at the chemical potential, so they will immediately respond to a pressure release, and hence I don't see a way to have this metastable state recovered to ambient pressure. We've not tried. It would not be easy, because going above 100 GPAs, diamonds do form micro cracks, which upon releasing pressure become macro cracks, and hence the diamonds explode. And then you would have to look in the gravel whether you can find the sample. So it wouldn't be an easy one, but we've not yet tried, and I don't have much hope there for superconductors.
Thank you.
Okay. Any more questions about the superconductors? Are we doing on time?
Question, where do we start?
Oh, another 10 minutes or more.
It's nickel disulfide for the. Yeah, no worries. Is that coming back? Yeah. Right. So another way to involve high pressure research is to think about tuning electronic properties, specifically tuning bandwidths. In the simplest case, if in the simplest tight binding models, you know about the bandwidth to be related to the overlap integral, and of course overlap integrals will depend on the atomic distances, and that's exactly what we can tune with high pressure. And of course the most important model that we use for correlated materials is the Hubbard model, where the hopping or the bandwidth of the electronic bands is quite important in the balance together with the Coulomb repulsion. And one important concept is that of the Mott insulator, which you get at half filling. That when you would expect this by pure non-correlated arguments to be in metal, you nevertheless get an insulator due to the strong Coulomb interaction, and hence a gridlock of electrons. So we can study this with high pressure, and in fact we've done some measurements on nickel disulfide, which is a Mott insulator at ambient pressure. As you cool down, you get some magnetic transitions, and you can turn it into a metal above about 3 GPa, which does necessitate the use of diamond or other gemstone Anvil cells. We've done exactly that. So we're asking ourselves, what's essentially, can we probe Luttinger theorem here? The argument being that if you think about the half-filled non-correlated band, there's different ways to think of how we form a Mott insulator with the two split bands. And in particular, there's both the Brinkman-Rice and the DMFT pictures tell us that we expect a peak in the density of states, but preserve the Fermi surface volume. So we've studied this by doing quantum oscillation measurements under high pressure. We specifically used a contactless method, which nevertheless requires electrical leads into the pressure cell, but it's contactless to the sample. The sample is sitting inside a coil. This coil is then, you can see it here in the picture, sitting in the gasket. This is the indented area of the gasket. But you can also see the two wires connecting to the coil coming out. They are insulated against the gasket. And then this coil is part of an LC circuit, which is driven by a tunnel diode and hence maintains its oscillation. Now, the natural frequency, the resonance frequency of this oscillator will depend on the inductance of the coil, which itself depends on the skin depth of the sample, because essentially the volume that's available for the coil to create a B field is limited by how far you can go into the sample. So that's how you get a link to the skin depth. And the skin depth itself is, of course, related to the resistivity of the sample. So it's a contactless probe of the sample of the resistivity. So we can do this at high pressures, and we do see quite beautiful quantum oscillations in nickel disulfide. So we start with a sample which is, of course, insulating at ambient pressure, but once we go into the metallic phase, we see beautiful quantum oscillations. So it's the frequency of the tunnel diode which shows these oscillations, but as I said, this is proportional to the resistivity. The Fourier transforms show us some nice high frequencies of the order of 6 kilotesla, as well as some low frequencies. This highest frequency is most easy to understand. It corresponds quite clearly to a cube-like Fermi surface in this in nickel disulfide. So this is a rotation study where we observe how the frequency increases as we rotate the whole pressure cell, including the sample. All of this is done at very high magnetic fields, and it fits quite nicely with the DFT calculations here overlaid as the solid line. So we've got a good understanding that we have got the Fermi surface, and in particular that it looks like the DFT U equals 0 Fermi surface.
So this is, so you mentioned there is also a magnetic order that is similar.
Yes.
Taking into account the different order, or
actually it is a non-collinear order in the unit cell, so it is not leading to a folding of the boron zone. So hence we can just, as a first approximation, we can very well simply use the non-magnetic structure to calculate the Fermi surface.
There was magnetism on either side. Just to could see the phase diagram one more time. So where are we in the phase diagram?
Of course, we are here in the metallic side. In order to observe quantum oscillations, they are only present here.
And that magnetism is the one that is
Non-collinear, yes.
Okay. And is there any resemblance, just out of curiosity, between the magnetism on the other side?
I don't know on the top of my head, to be honest.
Maybe you would expect they don't have to have anything in common.
The zero pressure magnetization definitely shows some weak ferromagnetic hysteresis. So in that sense, it is already different, but I'm not sure whether there's above it an antiferromagnetic state with the same structure like in the metallic phase. I would have to look it up. I don't know.
So what is the logic now of Luttinger's theorem? We are comparing what with what? Just for me to understand.
What I'll be looking at is whether or not the Fermi surface on the approach of the metal insulator transition remains the same.
I see. Okay.
And yeah, that is already to some extent visible on here, and that the high frequency remains. And if we look at this in more detail, the frequency in fact only depends very weakly on pressure, and this solid line that I've put through here is exactly what you expect based on the compression of the material. So it tells us that the Fermi surface does remain large right up to the insulator transition. At the same time, we can of course use the quantum oscillations to measure the effective mass, and we observe that there's an increase of about a factor of 7 between the highest pressures where we've looked at this down to the lowest pressures close to the insulator transition. We can fit this. You can already see that the line appears to diverge not at the metal insulator transition, but into the insulating state. It's not completely surprising because the metal insulator transition is first order. So there is a coexistence region to it where the true divergence is probably somewhere in that coexistence region.
But you're saying despite being first order, it still resembles to quite significant degree
this divergence. And that's also in agreement with single-site DMFT calculations, which predicted to be first order and nevertheless to have a divergence in the effective mass. Right. So that's the highlights of high pressure research that we've done over the years. So I've shown you yesterday already some results and today a few more. We can do new compounds like H3S. We can do new phases like superconductivity in H3S or the metallic state in nickel disulfide, which only exists at high pressures. We can tune these correlated states. We can look at the interplay of states like I've done yesterday, niobium diselenide, or completing states or mutually stabilizing states like in the elemental sulfur. And most importantly, we can put clean samples in our cells and maintain their cleanness, at least for nickel disulfide. H3S seems to be quite clean. Lanthanum H10, I've made the case, is a bit more tricky, but that's the synthesis in the first place that's tricky. All right, with that, I'll mention that mostly here the collaborators that have been working on the hydrogen sulfide with me. So this is a picture of my former and current students and collaborators at Bristol. A lot of the hydrogen sulfide work was done by Owen Moulding, as well as Israel Osmond. Oliver Lord here is working in earth sciences in Bristol. He is set up, he has the setup to do the laser heating. So without his support, we wouldn't have been able to synthesize these samples. And we're working together with people at the X-ray facilities, Simona and Sally from Diamond Light Source, as well as the group from the DESI synchrotron in Hamburg, which were critical for the X-ray diffraction. And we've done high field measurements at pulsed field and DC facilities in Europe, both on the hydrides as well as on the nickel disulfide and other compounds. All right, with that, I'll finish and thanks for your attention.
More questions?
Naive curious question. How do you measure temperature at high pressure?
We immerse the whole pressure cell in a bath or couple it well to a thermal bath and have it sitting in vacuum. So the thermometer is typically attached somewhere on the cell body, but we assume that we've got equilibrium between the sample and the thermometer on the cell body, where we cross-check this, for instance, by doing temperature sweeps up and down and looking at full relaxation as we change temperature.
Because I was wondering, you could go out of equilibrium.
Yes, and we check that we don't. Yeah.
Okay, thanks.
Diamond, luckily, is a good thermal conductor, so that helps.
Okay.
Why is nickel disulfide superconducting?
There's two places to hope for superconductivity, either close to the metal insulator transition, or in fact, even at the quantum critical point of the antiferromagnetism. Philip Niklowitz, who was here yesterday, has indeed done quite a long time ago transport measurements to lowest temperatures out here, did not find any superconductivity, despite the A coefficient of the resistivity having a peak there.
That's not proper behavior, right?
No. Yeah, we should punish the samples.
Yes.
Should be told off for it. Weak ferromagnetism, because it's a small moment.
The antiferromagnetic phase boundary above, you haven't extended it to the right or the left. other data points or other people's data points that extend that phase boundary?
That's all we've got is on here. This is based on a small kink in the derivative of the resistance. There's no magnetic measurements that have been done under high pressure. Mostly this is inferred from the analog phase diagram of nickel selenium sulfur, where part of the sulfur was replaced with selenium. Now you'd think that would go the wrong way because it's larger molecules, but actually what it does, it increases the overlap of the sulfur dimers. By putting in selenium, you increase the overlap to the, and hence you do the similar bandwidth control that we're doing with pressure. And their magnetism has been observed as well and been studied with neutron diffraction and of course with magnetic bulk probes. And that's how the magnetism was established in the first place. And then in resistance, antiferromagnet signatures have been observed at high pressures and have been interpreted as the antiferromagnetism, including a peak of the A coefficient as you come to close to this 7 GPa. So one could, of course, look at this in more detail. One could try and there is some scope for looking at the most clean samples and with the best pressure conditions. Maybe again, maybe we're first to actually look with magnetic measurements, maybe even neutron scattering at high pressure to see whether the antiferromagnetism is really there.
If I take the TC curve, so the Mott transition curve seriously, then the entropy of the Mott insulator is higher than the entropy of the metal. Is there I mean, there are wonderful arguments I could talk about. This is proof for spin liquid behavior of massive spin-on Fermi surfaces or something like this. Or is there something? So is it hard to go further down because this bends over?
So ideally, in order to probe the transition there, you would need isotherms. That involves all these difficulties about solid pressure media, again, that I've alluded to earlier. So you would have to do an experiment where you actually take something which still behaves well at low temperatures. And that's pretty much only helium left. That makes things trickier because helium is more compressible, hence gaskets are less stable and all these things. So that's why it's not been looked at in all that detail. You could imagine that potentially, because if you've got a coexistence region, if you increase pressure at high temperatures, cool down at high pressures, and then release pressure, you could even maintain the metallic state maybe even further. So there's all sorts of questions, but it makes it very difficult in experiments because it needs extra apparatus to take the load off, and then you need well-behaved pressure media and pressure cells for that. I think Andrew was waiting for one.
Back to the first part of your talk, it seems that the pressures you can get to in the end, material limited. You have diamond, there's not much else you could use. Do you see any prospects for increasing these pressures by next generation designs, and what's the limit?
Some of it, I think if 10 years ago, nobody would have suspected that one can go to 1000 GPa. So I think the technology of high pressure research has already pushed the boundaries quite a bit. So initially when Bridgman got the Nobel Prize for the invention of the diamond anvil cell, they were happy to achieve 10 GPa with it. And then culettes were made smaller to achieve higher and higher pressures. Bevels were introduced to go above 100 GPa. Then the toroidal design was introduced to go to 450 GPa. And it's only in the last 20 years that these double stage diamond anvil cells were made for going to up to 1000 GPa. So I can't predict what will be the next stage to push the boundaries further. It does, of course, always come along with smaller sample sizes. So we've not really escaped P equals F over A here. That's certainly true. But what we have done is miniaturizing experiments with putting electrodes on anvils and all sorts of that. So we could hope to improve that further still.
You just took that line. How there's a minimum size that you might, well, one.
This is a
atom
logarithmic
size.
axis.
I know it is.
So
I mean,
technically
how
there's
far
no
can you go
limit.
and say sensible things?
Yeah. Yeah. Yeah, I think it's the practicalities which limit us more than just playing. There are groups which, of course, are just interested in pressure records, and they have invented these double stage cells. It's the practicalities of doing meaningful measurements. So, for instance, if we're interested in superconductors, we want transport measurements that will hold us up much more than this pressure boundary. Yeah.
Will that be enough to produce metallic hydrogen technology here?
It is predicted to be enough, yes. Metallic hydrogen is expected. Okay, this has also shifted. In the early days of Ashcroft making the prediction, it was expected to happen at 40 GPa. And people went there, it wasn't there. So then the prediction was shifted further and further, and it continues this way, right? So metallic hydrogen was, there's quite a back and forth between experimentalists, somebody claiming to have seen metallic hydrogen, and then other people disputing it, and in fact probably being right, and then the theorists going back to the board and seeing, we've not included this quantum effect or that, and saying, okay, actually it's got to be even higher pressure. Currently we're expecting it at about 500 GPa. And yes, these double stage anvil cells can go there, but you are still limited in what you can do. In order to prove that it's metallic hydrogen, again, you would want transport measurements. And that requires electrodes, and that's not yet been successful. It also requires insulating gaskets, and it also requires to make sure that the hydrogen doesn't diffuse out of through the insulation, which is another problem. Hydrogen is quite volatile. It diffuses through bore nitride very easily. It diffuses even into the diamonds, makes them brittle and crack. So there's all sorts of difficulties there.
Any further questions? I can't see behind. Is that someone there? No. Well, let's thank Sven for great talk.
Thank you.